It's working.
Yeah, it's good. It's good.
No, it's not.
Yeah, it's good.
It's working. Okay, let's see if we can start. The principles that a logic should satisfy if it wants to do plausible reasoning. That's the idea behind this. Non-monotonic reasoning, at least from the AI community, artificial intelligence community, started with two seminal papers in 1980, and it's gone on from there. What NMR does is reason with unquantified uncertainty. So we're not certain, we don't just have facts, we have woolly statements, but they're unquantified. So no numbers, no probabilities, no certainty factors, no numbers, no numbers, no numbers. Instead, we use words like woolly, usually, typically, probably, where probably is ordinary English, not as in probability theory, probably. Okay, so that's what NMR does. Plausible reasoning, as I see it, does this. It assesses, it assesses if something is true more often than not, in which case it says, yeah, I'll go with that. It can prove it. Or it assesses if the evidence of something outweighs the evidence of things that are against it. Many logics have been invented since 1980. None of them claim to do plausible reasoning. All of them claim to be able to reason with this likely, usually, typically information and get the correct or proper outcomes. That's what they all claim. To me, that's the same as plausible reasoning. I started developing my own plausible reasoning logic, and as I was doing this, I naturally looked at the many logics that have been invented, and I kept on finding that they didn't do the right things. So I thought, I think it's time to define plausible reasoning or something like that. Well, I couldn't, but the best I could do was to get some principles that if you want a logic to do plausible reasoning, you really should get them to satisfy these principles. And the paper gives 15 principles and 5 important examples of plausible reasoning. Some of the principles are necessary. Some of the principles are just desirable. So here are the 15 principles. No, I do not intend to go through all of them, nor do I intend to read them. But I would point out principle almost 16. It's a very important one. It says that if you have a plausible reasoning situation, puzzle, and there is a correct answer, there isn't always, but if there is a correct answer, then we would like your plausible logic to get that correct answer. So why don't I put that as a principle? Basically because no logic I know satisfies the principle. So I didn't want to say, my logic satisfies the first 15, but it doesn't satisfy the 16th one, because that sounds a bit dumb. However, we can use it. If I present you with an example and you play your favorite logic on it, and it gets the wrong answer, then I can say that in that particular case with that example, it gets this unnumbered principle wrong. So that's why that's sneaking in there. Okay, the first thing that everyone seizes on is that plausible reasoning must be non-monotonic. And indeed it must. Here is an example. Suppose we know that emus are birds. That's a fact. Emus do not fly. That's a fact. Birds usually fly. That's a usually woolly statement. Tweety is a bird. That's a fact. Tweety is an emu. That's a fact. Now, if we just take statements 3 and 4, birds usually fly, Tweety is a bird, then we should conclude that probably Tweety flies. It's likely that Tweety flies. But if you add new information, like the rest of the statements, then we are unable to sensibly draw that conclusion. That's what non-monotonic means. It means if you add more information, some previous results may have to be retracted. So certainly we need that. Another principle that is handy, because it's not quite classical logic, is if F is likely, and I use the term F is likely to mean if your logic proves F. So if F is likely and G is likely, then the conjunction F and G might not be likely. So if your logic satisfies this conjunction property, it's not going to be good enough. Here's an example. It's a famous example. I call it the three-lottery example. You have a bin. If you're old-fashioned and you're dealing in probability, bins are called urns, but I have a bin anyway. And they have three balls. One is red, one is green, and one is blue. And we have to select one at random. So selecting R is not likely. You got a 1 in 3 chance. Not selecting G, that is likely. Not selecting B, that is likely. But the conjunction of those two likely things, that is, not selecting G and not selecting B, that's not likely. So this shows that that non-conjunctive principle should be adhered to. Yes. The next one is one of my favourite ones. Consistency. Some time ago, a person listed 14 or so things that a person, not a logic, that a person who does plausible reasoning should satisfy. And I think condition 11 said that when you deduce a whole lot of things, they should all be consistent. And indeed, one of the original seminal papers had that as a basic fundamental tenet, that whatever is proved, the whole lot, the whole set of things that are proved is consistent, which seems reasonable, providing you're classical and don't think too much. So that's what this says. All our situations can be phrased in the following structure. We have a whole lot of facts which are true and not to be disputed. And then we have a whole lot of, those facts are satisfiable and closed formulas in, say, some first-order language, something like that. And then we have a whole lot of things which are plausible. They might be rules, they might be defaults in default logic, whatever. But they don't have to be formulas. Now, if F is provable and if G is provable, then it turns out that the set containing F and G should be satisfiable. Not only that, it should not contradict the facts. So this is satisfiable, but it should not contradict the facts. So the whole lot should be satisfiable. Very traditional, very uncontroversial. But surprise, surprise, this is not true when you take more than 2. So consider our bin with 3 balls, red, green, and blue. Not selecting R is likely. Not selecting G is likely. Selecting R or G is likely. So we've got 3 likely things, that is 3 things which our logic should be able to prove. But the set of those 3 things is unsatisfiable and hence not consistent. So consistency is very limited. 2 things, yes. 3 or more, no. And that is a big shock. Okay. Most logics that I know about have one proof algorithm. They have one way of proving things, and that's it. Take it or leave it. That's not really good enough when you deal with usuallys and plausible reasoning. Consider the following example. There is evidence that A is likely. There is evidence that not A is likely. So we don't know about A. A is ambiguous. Okay, so A is ambiguous. Now let's look at B. There is evidence for B, so B is looking good. But if A is accepted, then there is evidence for, or that is evidence for not B. So the question is, should your logic be able to prove B, or should it not? Here's a hint. In the English legal system, you have civil cases which give guilt on the balance of probabilities. Now, on the balance of probabilities, you should be able to prove B, because we have evidence for B, but the evidence against B is definitely weaker. And so on the balance, you should be able to prove B. That being able to prove B is called ambiguity blocking, because the A, which is ambiguous, has been blocked from contaminating further on. On the other hand, in the English legal system, you have criminal offences, and there you need stricter proof. You need beyond reasonable doubt. Now, certainly there's reasonable doubt about B. A is 50-50. So not B is got a reasonable chance of being the case. And so you shouldn't be saying, B is okay. It might not be. So if you are cautious, then you should not, you should propagate the ambiguity of A so that B becomes ambiguous. So you need at least two different algorithms: ambiguity blocking, ambiguity propagating. The other thing that at least I, as an old-fashioned mathematician and logician, am used to is that you have two truth values. Yeah, I know there are other things, but basically we have two, right? It's true or it's false, end of story. Well, not so fast. When you have usuallys, you need a truth value that says it's more likely to be true than false. Sort of usually true truth value. You also have one that says it's usually false. You have a usually false true value. But there are many cases in which you have a statement and it's not usually true and it's not usually false. It's 50-50. You can't tell. So you need at least three truth values. So that's all the ones that I wanted to go through, and I might not run late. So some years ago, I finished inventing propositional plausible logic, and to my great delight, if it didn't, I was going to change things, so it would. It satisfies all 15 principles and gets the correct answer to all the 5 puzzles in this paper. I spent some time looking at every non-monotonic logic I could find. This is in 2019. And every logic I could find, to me, was faulty. Either it got the 3 lottery bin of 3 coloured balls wrong, or else it got one of those 3 principles that we've just talked about wrong. So they may do, let's say, default reasoning, but it's not plausible reasoning. In other words, they get some answers wrong. There are some logics that are very weak, that seem to be okay, and they only deal with literals. So no and, no or, and certainly no implies. So that's that. Okay, if you were wanting to do some extra homework, what principles have I missed? Find some more. If you want a really, really hard problem, find more principles. If you can't, then prove that the 15 I've got are all that is possible. I've got one plausible propositional logic that does plausible reasoning. Create your own. You have an advantage now. All the other inventors didn't have these 15 principles and examples to use to model their understanding on, but now you do. What am I doing? I'm trying to convert the propositional logic I have to a first order logic, and that's where I'll end it. And I've got 2 minutes left.
I think that we pushed everything by... so this is really the end of the talk?
This is really the
okay.
This is really the end of the talk.